So finding the efficiency of a or a steam engine is a little bit complicated. To start, we know that the efficiency is equal to 1 minus the energy that we deposit into the cold bath divided by the energy that we harvest from the hot bath. So to get this, it's kind of a complicated equation. Let's check out the smartboard. Alright, so it's 1 minus the heat at point 4 minus the heat at point 2 over the heat at point 3, that's point 3, minus the heat at point 1. So we can say that the heat at point 2 and 1 are equal because the pump doesn't add any enthalpy. By the way, every time I've said heat, I meant enthalpy. So basically what we're looking for is the ratio between this distance and this distance. Okay, so the enthalpies are characteristics of steam and water, and so to find them we need to look them up in our handy dandy steam tables. So this is the steam table for saturated water, and this is the steam table for superheated steam. We need both of them because H1 is saturated water steam system, and H3 is superheated. So to start, let's do an example because it's kind of impossible to explain without one. So let's say in our steam system we have a maximum temperature of, so at the end of the boiler our water is at 600 degrees. The highest pressure we reach is 300 bars, and the minimum pressure is 2.3 bars, or 0.023 bars. So to find H1, our enthalpy right after the condenser, we check it out. So 0.023 bars, we need the enthalpy of the water, so that's 84. So H1 is 84. Now to find the enthalpy at H3, we use our superheated steam table. And so we know that the pressure is 300, we know that the temperature is 600, so 6.23 is our entropy, and 3,444 is our enthalpy. Alright, so we know these two, but to find H4 is a lot more complicated, but we know that the entropy at 4 is equal to the entropy at 3, and the pressure at 4 is equal to the pressure at 1. So first, let's try and solve for the entropy, because we need a gas-water mixture that has the same entropy. So if we check out our saturated steam table, we can see that there's some mixture of these two values, because we're at the low pressure now, because we're after the turbine. There's some mixture of these two values that will give us the value we need, which is 6.233, I think. Yeah. So we use this equation. The entropy at 3 is equal to the water entropy at our minimum pressure plus the steam entropy at our minimum pressure. And then X is just represents how much, this is how much is water, and then this is how much is steam, this expression. So if you solve it, you get 0.29 is water and 0.71 is steam. So you plug that back in, except for this time, instead of using entropy as your coefficients, you use an enthalpy. So we already know that the enthalpy of water at that pressure is 84, and then we can look up the enthalpy of heat, or the enthalpy of steam, is 2538. So we solve this for H4, and then we get 1824. Plugging all those into this equation right here, we get an efficiency of 48, which is reasonable. So it's much simpler with gasoline and diesel engines. Basically, it's the same idea. The efficiency is equal to the work that we extract divided by the energy that we put in. So for gas, it's 1 minus the compression ratio. For a typical engine, the compression ratio is about 1/8, so that means that when it's compressed, when it's like all the way down, it's about, or the piston is all the way compressed, it's about 1/8 the volume of it when it's all the way expanded, times the adiabatic exponent, which is explained in section 1.5, or exponentiated by the adiabatic exponent. So if you plug these numbers in, you get 0.56, which is reasonable. I think that's it. Thank you.